All right, let's get right into it. From streaming your favorite show to checking your bank balance, our entire digital life is built on this powerful, pretty much invisible architecture. Today, we're going to pull back the curtain on the magic that makes it all work: distributed systems.
I mean, really think about that for a second. How can a single app, say a huge streaming service or a social media platform, handle millions, and I mean millions of people all at the same time without just collapsing? It feels like it should be impossible for just one computer, right? Well, that's because it is.
The secret sauce is this amazing idea that basically turns a whole army of separate computers into one single super powerful system. Let's break down how that works.
So, what exactly is a distributed system? Well, the formal definition is right there, but think of it like this. It's a bunch of totally separate computers that work together so perfectly that to you, the user, it just looks and feels like one solid thing. They're constantly sending little messages back and forth to stay in sync. Kind of like an orchestra, right? You don't hear the individual violins and cellos, you just hear one unified piece of music.
Now, making this happen is not easy. It comes with some really tough challenges. You've got to deal with concurrency. That's just a fancy word for tons of different things all happening at the exact same time. Then there's the fact that there's no single master clock. Every computer has its own sense of time, which can get messy. And maybe most important of all, you have to plan for failures. If one computer in the network goes down, the whole show has to keep on running.
So, to wrestle with all those challenges, engineers build these systems based on a few key rules, a few core principles. Let's look at what actually makes a distributed system a good distributed system.
You can boil it down to four main things. First, transparency. It has to hide all that complexity. You shouldn't have to know there are hundreds of computers working for you. It just works. Openness is also key. You want to be able to add new parts or services later without having to tear the whole thing down. Fault management is that ability to handle failures gracefully. But then there's the big one, the holy grail, scalability, the system's ability to grow. So how do you grow? How do you handle more and more users? This image lays it out perfectly. On the one hand, you have A, which is called vertical scaling. That's like just buying a bigger, beefier computer. You upgrade your laptop with more RAM, a faster processor, but you're going to hit a wall eventually. Path B is the superpower of these systems, horizontal scaling. Instead of making one machine bigger, you just add more machines to the group. This is how the giants of the internet handle growth. They just keep adding more computers to the pile.
But hang on a second. If you have all these different computers, maybe they're even running different operating systems, how in the world do they actually communicate? It seems like they'd be speaking different languages. Well, there's a really clever solution for that. A sort of digital glue that holds everything together.
And that glue is called middleware. It's this special layer of software that sits right in the middle of everything. You can think of it as a universal translator. Its whole job is to take messages from one part of the system and make sure any other part can understand it, no matter how different they are. It smooths over all the differences.
And you can see it perfectly in this diagram. That middleware layer is like a central highway for communication, connecting all the different computers and applications. Without it, you just have a bunch of isolated parts. With it, you have a single, coherent system. It is absolutely the unsung hero of distributed architecture.
Okay, so now we get the core ideas, but what do these systems actually look like? Well, architects don't just build them randomly. They use a few common blueprints or design patterns depending on what the system needs to do.
The one you've probably heard of is the client-server model. The easiest way to think about it is like a restaurant. You are the client. You make a request. You order your food. That request goes to a central, powerful server, the kitchen. The kitchen has all the ingredients and does all the hard work, then sends the result back to you. Simple, centralized, and really common.
But there's another way to do it, peer-to-peer, or P2P. In this model, there is no central kitchen. It's more like a neighborhood potluck. Everybody is a peer. They're all equals. Everybody brings something to share, and everybody can take from what others brought. All the resources are shared directly between all the participants. So, what's the trade-off? Well, with client-server, you get centralized control, which can be simpler to manage. But that server can become a major bottleneck. If the kitchen gets overwhelmed, everyone's waiting for food. Peer-to-peer, on the other hand, is decentralized. That makes it way more resilient. If one person leaves the potluck, the party doesn't stop. The downside is that coordinating all those peers can get a lot more complicated.
A perfect real-world example of P2P is something like BitTorrent. When you download a big file, you're not actually grabbing it from one main server. You're downloading tiny little pieces of it from dozens, sometimes hundreds of other users, your peers. And at the same time, you're automatically uploading the pieces you already have to other people. It's this massive collaborative sharing system.
Now, there's one more key blueprint to know. It's traditionally been called the master-slave model. You should know, though, a lot of the industry is moving toward better terms like controller-worker, which I think describes it better. The idea is you have one master or controller computer that acts as the brain. It takes a massive job, breaks it into tiny little pieces, and hands those tasks out to a whole bunch of worker computers to do the actual work.
And one of the coolest examples of this ever was the SETI at Home project. A central master server had all this astronomical data from radio telescopes. It would send tiny chunks of that data out to thousands of regular people's computers all over the world, the workers. And those PCs would analyze the data in their spare time, looking for signs of alien life. It was basically a way to build a global supercomputer out of regular home desktops. Just brilliant.
Whew, okay. We have covered a lot of ground here, from the basic concepts to the actual blueprints. So, let's step back and just boil it all down. What are the most important things to remember?
Here's the bottom line. First, remember that distributed systems are all about making many computers act as one. Their absolute superpower is horizontal scalability, growing by just adding more machines. The magic that makes this possible is middleware, that essential glue acting as a universal translator. And finally, architects pick the right tool for the job, using blueprints like client-server, peer-to-peer, or controller-worker. These are the fundamental ideas that quietly run the world we live in. And that really leads us to a final big question. As our world gets more and more connected, as everything from our cars to our coffee makers comes online, which of these blueprints do you think is going to build our future? Will it be the centralized control of the client-server model, or the decentralized resilient power of peer-to-peer? Definitely something to think about.